Okay, this is the 11th and last video for IB Astrophysics. We're going to be looking at more cosmology today. Remember, in the last video, we said that the universe is expanding, which we can tell because galaxies are moving away from us. The farther they are, the faster they're moving. And that raises some questions. The first one is, well, is the universe ever going to slow down, stop, and come back on itself? And there are several different cases that we can look at. What this graph shows is time on the x-axis, and this is now, we know we don't actually know how big the universe is, but we'll just say however big the universe is now, that's 1. And then the relative size of the universe on the vertical axis. And we know about how fast the universe is expanding. And then these 4 different graphs show 4 different possibilities for the universe. In the orange case here, the universe started out moving very fast, has been slowing down, and will eventually reach a maximum size and turn around. We call that possibility a closed universe. And the time when everything comes back to the same location is sometimes called the Big Crunch. The other possibility, which is the blue one, is an open universe, where the universe will continue to expand forever. And then there is also what's called the flat universe, where the universe will continue to expand, but as time approaches infinity, its velocity will tend to 0. And so the flat universe is a parabola. This graph is a sideways parabola. The other case is that the universe is actually accelerating, and that's called an inflationary universe. You don't really need to know about that at this point. And you don't need to know what these numbers are here yet either. But you need to know the difference between a closed universe, an open universe, and a flat universe. Closed universe will eventually turn around and crunch back on itself. Open universe will keep expanding forever. Flat universe will expand forever, but its speed will approach 0. And that's what I've written here. Now, which is the case depends on how much mass there is in the universe. Because if there's a lot of mass, there's going to be strong gravity, and the universe everything will attract, and it will eventually pull back on itself. If there's not enough mass, it'll just keep going, and we'll have an open universe. And we can actually calculate the critical density using the idea of conservation of energy. Now, conservation of energy would say that, to begin with, we have a certain amount of kinetic energy and a certain amount of gravitational potential energy. And then if the universe is flat, once everything's infinitely far away, the speed will be 0, and so the total energy will be 0. Now you solve, so you take this equation, and then you say, well, on average, the critical density of the universe is equal to the total mass of the universe divided by the volume of the universe, assuming the universe to be a sphere, which is actually not a terrible assumption, and also using the fact that from Hubble's law, the speed of receding galaxies is equal to Hubble's constant times their distance. And when you substitute these 2 equations into the first one, what you get is that the critical density rho naught equals 3 times the square of Hubble's constant divided by 8 pi g, where g is the gravitational constant. And based on current estimates of the Hubble constant, this has a value of about 10 to the minus 26 kilograms per cubic meter. That means that if the average density of the universe is such that it has 6 or 7 hydrogen atoms in every cubic meter, the universe will be flat. If it's more than that, so if the critical density exceeds, or if the density exceeds the critical density, then you have a closed universe. If the actual density is less than the critical density, we have an open universe. If rho equals rho naught, we have a flat universe. I didn't work out the details of the algebra here, but I encourage you to, on your own as an exercise, also a good way to review for the exam. And so the question is, well, which is it? And it turns out that even though that critical density is a very small number, the universe is probably nowhere near the critical density. If you look at all the stars and gas clouds and so on that we can see, that amounts to roughly 4% of the critical density. Now, but we also know that there are things out there that we generally term dark matter. They don't interact with light, but they do interact gravitationally, and there's a number of ways we know these exist. It turns out that galaxies don't have enough mass to hold together unless there is additional mass that we can't see. And that, because we don't know much about it, we don't really know how much there is, but estimates are that this would account for roughly another 25% of the critical density, which means that the total density of the universe is still less than 1/3 of the critical density, and it appears that the universe is open. So there you go. The universe is probably open. There is some dark matter out there, but it's not enough to make the universe not open. But now there's also some data that seem to suggest that distant galaxies are not only moving away from us, but accelerating away from us. They're actually speeding up. Whereas all three of the models of the universe that we discussed, open, closed, and flat, have the universe slowing down. The question is just how much will it slow down? And at this point, scientists have something that they call dark energy, which, as far as I can tell, is just a word for something out there and we don't know anything about it. But it appears that space itself, or something like that, wants to expand. There's like some kind of outward pressure. And it's weird, and you don't really need to know much about it besides that the universe is probably accelerating. And that's what we call the inflationary example on this page. Now, the last thing we need to talk about is the Big Bang Theory. And the Big Bang Theory is the currently accepted theory. Like most popular names for theories, the Big Bang Theory started out as an insulting term. But basically the idea is the universe started out very hot, very dense, and very small. And as it expanded, it was an adiabatic expansion, because you can't really have heat going anywhere from the universe. It cooled, just like when you let air out of a spray can rapidly, it cools. And so at the beginning, you had very high temperatures and probably something called a quark gluon plasma. As the universe cooled, what happened was the quark gluon plasma, in a sense, froze or condensed into nuclei and electrons. And then, as the universe continued to cool, what happened was the temperature became low enough that the electrons could grab onto the nuclei and form neutral atoms. The time when this would have occurred is basically when the average kinetic energy of a particle, so the average kinetic energy, remember, is related to the temperature. The average kinetic energy of a particle becomes less than the ionization energy of hydrogen, which is about 13.6 electron volts. Because if the average kinetic energy is larger than that, what happens is that two atoms will collide with each other and their electrons will get knocked off and you'll have ions again. Now the other thing about this is that this probably occurred when the universe had an age of around 300,000 years. But as soon as the universe was composed mostly of neutral atoms instead of nuclei and electrons, which are charged, is that photons interact, meaning light, much more strongly with charged particles than with neutral atoms. Remember, if a photon hits a neutral atom, it will only interact with that atom if it happens to have an energy equal to one of the energy gaps. And so when the universe turned into neutral atoms, that was when the universe became basically transparent to light, where photons could go a long distance without interacting with anything. And that is important because it led to something called the cosmic microwave background. When the universe became transparent, roughly 300,000 years of age, there were photons everywhere that were left over from the photons produced in the early stages. And then as the universe expanded, what happened was that space was stretching and all of those photons got redshifted. And they got so far redshifted that they're no longer visible. They were originally UV, basically. And they got redshifted through the visible and through the infrared and into the microwave region. And so if you point a radio telescope anywhere in space, you see a blackbody spectrum with a temperature of about 3.5 kelvins. It's plus or minus a few millikelvin. So very cold, but anywhere you look, you see the spectrum, and it looks about the same any way you look, and it doesn't come from any object. It's just there. It's left over from the Big Bang, and it's the single most important piece of evidence for the Big Bang theory. And it's a relatively recent discovery, too. I think the satellite that discovered it those results were published in 1995. So the Big Bang theory was not widely accepted until the 1990s. So there are very interesting and very important changes still being made in physics. What you need to know, you need to be able to describe the difference between an open, closed, and flat universe. You need to know what the phrase critical density means. You need to be able to draw that graph of the size of the universe versus time. You need to know what the Big Bang theory says and be able to describe cosmic background radiation.